Hello, dear students. Today we are going to discuss a very important topic, and that is the splitting tree or the coupling tree. And later on, we will discuss how we can calculate coupling constants for different multiplets that we see in the proton NMR spectrum. So let's start our today's topic. Splitting trees or coupling tree is very important when it comes to proton NMR spectrum. It is because of the fact that it gives you information about the coupling constant calculation, which arms or which peaks you have to take into account while calculating the coupling constant, right? But before that, it is important to know how to draw the coupling trees. So coupling tree or splitting tree is actually like an inverted signal. So I have drawn here a few hypothetical structural features, and we will try to draw the splitting trees or the coupling trees for these situations. So here we have a situation in which we have two protons, HA and HB. I have labeled them as A and B just to indicate that these are magnetically inequivalent protons, which means that the coupling between them can be observed and their peaks will be split because of each other in the proton NMR spectrum. So these two protons, HA and HB, they are vicinal to each other, meaning they are attached to adjacent carbon atoms. And because they are magnetically inequivalent, they will couple with each other, or their coupling will be observed. So HA will be split into a doublet because of HB according to n+1 rule, and HB will be split into a doublet because of HA, again according to the n+1 rule. So both HA and HB will appear as doublets. Now we will see how we can draw the splitting tree for this system. So in each of these cases, we will talk about, or we will focus on the proton HA. So here is the proton, and it has one proton in the vicinity. That means its signal will be split into two, and it will give a doublet with equal intensities of the arms or the peaks. Now, as I told you earlier, that the splitting tree is just like an inverted signal. So you can draw an inverted signal on top of this, and that will be the splitting tree. But how? How to draw it? See, we have a proton. If there is nothing in the vicinity of this proton, it will give a singlet. So you draw a single line, and now because under the given conditions or situation, this HA has one proton in the vicinity, so its signal will be split into two because of HB. Now this single line will be split into two. So it goes to the left and it goes to the right, or it is split equally to the left and to the right, right? So if you take its center here, this center is equidistant from the left and also from the right, right? So the distance from the center to the left peak and to the right peak is exactly similar, which means that this line, this single line, was split equally to the left and to the right, giving rise to two peaks, and that are the peaks of the doublet, or the arms of the doublet. Now the separation between these two peaks is known as the coupling constant, or the J value in Hertz. The separation is measured in Hertz. Now this is a simple splitting tree. Let's discuss a slightly more complex triplet. So if we have a proton HA and it has two protons in the vicinity which are magnetically equivalent to each other, like these two, but they are magnetically inequivalent to HA. So the signal of HA will be split into three according to n+1 rule, and we will get a triplet, while the signals of HB will be split into two because of HA. But because we are focusing on HA only, it will give a triplet, and we will see how we can draw the splitting tree. So each of these Hb protons will couple with Ha. So Ha first couples with the first Hb and then it couples with the second Hb. So let's see. You start with a single line, which means Ha doesn't have anything in the vicinity, but if it has some protons in the vicinity, then the signal will be split. So it has a proton Hb in the vicinity at vicinal position. So this single line is split into two lines like this, just as you saw in the doublet. The separation between these two lines is the coupling constant, that is the J value. But this Ha does not have only one proton, it has two protons in the vicinity. So it has another Hb here. It will also couple with the second Hb. Now because both Hb protons are magnetically equivalent, they will have the same coupling with Ha. The magnitude of splitting will be the same. So the splitting because of the first Hb will be exactly equal to the splitting because of the second Hb. So the first line was split into two, and now we have these two lines, this one and this one. Each of these two lines, which are produced because of coupling with the first Hb, will be split into two because of coupling with the second Hb. So this line will be split into two with the same magnitude as the first one, and this line will also be split into two with the same magnitude as the first one. But what happened as a result is that the central lines of these two splittings, they merge together. And why they merge together? It is because of the fact that this splitting J is exactly equal to this splitting J. Let's explain it with the help of some measurements. So for example, the first splitting is equal to 8 Hertz. So if this splitting because of the first Hb is equal to 8 Hertz, this means, as I told you earlier, that this splitting is equidistant to the left and to the right, which means that the distance from this line to the center will be equal to 4 Hertz, and the distance from the center to this line will also be equal to 4 Hertz. Right? Now, the splitting occurs because of the second Hb as well. Now, each of these two lines will split because of Hb. Now, the splitting is of the same magnitude because both Hb's are magnetically equivalent. So this splitting or splitting of this line will be of 8 Hertz, and this splitting will also be of 8 Hertz, which means that the distance between this line and this line is equal to 16 Hertz, and the distance between these two lines is 8 Hertz, and the distance between these two lines is also 8 Hertz. Now, why do these two lines merge together? See, to have a separation of 8 Hertz, this line has to split into two by going 4 Hertz to the left and 4 Hertz to the right. So it goes 4 Hertz in this direction and it goes 4 Hertz in this direction, so as to have a magnitude of 8 Hertz. Now, for a splitting of 8 Hertz, this line has to move to one side by 4 Hertz. So this line, this distance is 4 Hertz, and this distance is also 4 Hertz. So the total splitting is equal to 8 Hertz. We already saw that these two lines have a magnitude of 8 Hertz, or the splitting have a magnitude of 8 Hertz. And if you extrapolate these lines, they fall exactly in the center of these two lines or in the center of these two lines. So the distance between these two lines, the first two lines, is equal to 8 Hertz. And you saw that the distance from the center to this line is equal to 4, and the distance from the center to this line is equal to 4, and that is equal to 8 hertz, exactly equal to this 8. Right? Now, to split this line into two, it has moved 4 hertz to the right, and so it falls right in the center here. And the distance from this line to the center is equal to 4 hertz, which means it has moved 4 hertz. Now this line will also split into two up to 8 hertz, and it will move 4 hertz to the left and 4 to the right. So when it moves to the left, it covers 4 hertz, which falls exactly under this line or right in the center of these two lines. So they meet here. And that is why, because two lines merge here, the signal intensity is twice. And that is why triplet has a relative intensity of 1 to 1. 1:2:1. This is how you draw the splitting tree for a triplet. Now, we have HA here, and it has 3 protons in the vicinity, and all of them are magnetically equivalent to each other but different from HA. So HA will couple with all of the HBs, giving doublets, but at the end we get a quartet. Again, this is because of the merging of the lines. So we start off with a single line here, and this single line is split into two because of the first HB. The separation is J. Now this HA will also couple with the second HB. So each of these two lines, this one and this one, will split into two. And because the magnitude of splitting is the same, that is why the central lines merge again, just like a triplet. So here the intensities are 1, 2, and 1. And now we have 3 lines. But this HA will be split by the third HB as well. And again, the coupling constant or the magnitude of splitting will be the same as the first 2 splittings. So this line will split into 2, the central line will split into 2, and the fourth line, the last line, will also split into 2. This splits into 2 by J hertz. This splits into 2 by J hertz. And because they split equally, the central lines merge again. And this one also splits into 2. It merges this line, the central line merges again with this one. Now these two lines here, this one and this one, these are resultant of the merger of 3 lines. You see, here we have a merger of 2 lines, and these 2 lines with a double intensity merge another line from this splitting. So it has a merger of 3 lines, and that is why the intensity is thrice as the first and the last line. And that is why we have a ratio of 1, 3, 3, 1 for the quartet arms. But you may not have the same situation everywhere. You might have a proton that has 2 inequivalent protons in the vicinity. So for example, we have this situation, a hypothetical situation in which we are going to focus on HB here, and this HB has 2 protons in the vicinity, HA and HC. Now you can see that I have labeled them differently, which means that all of the 3 protons are magnetically inequivalent to each other. So HB will be split by HA, and HB will also be split by HC. But because HA and HC are magnetically inequivalent, the magnitude of splitting because of A and C would be different for B. So let's see this scenario. So first we have HB. We start off with a single line, and it is split because of HA first. And let's say the magnitude of splitting is shown by J1. Now it also splits because of HC, or it couples with HC as well. So we have these 2 lines, and each of these 2 lines will be split into 2 because of HC. Because HA and HC are magnetically inequivalent, the magnitude of splitting will be different. It will not be exactly similar to J1, but it might be smaller or larger. But if it is smaller, you see that each of these two lines, this one and this one, is split into two, and the central lines here do not merge because the distance they travel or cover while splitting is not exactly equal to this one. So if, for example, this splitting is 8 hertz and this splitting is 6 hertz, let's analyze it. Half of 8 is equal to 4, right? So you bring the center here, down here. This distance from the center to this line is equal to 4 hertz. Now to have a splitting of 6 hertz because of HC, these lines have to move 3 hertz to the left and to the right. So when they move 3 hertz to this side, they do not reach this center because this center is at a distance of 4 hertz from this line or the center of this doublet, right? So we still have 1 hertz of gap between these two, the center and this line. Similarly, to have a splitting of 6 hertz here, it has to move from the center by 3 hertz. But to join here at the center, it has to move 4 hertz. And so still we have 1 hertz of gap. So the gap between these two lines is 2 hertz. And that is the gap which keeps them separate, and we do not have a triplet. In fact, we have a new signal that is known as a double doublet or doublet of a doublet. In short, we call it DD. So when you have a DD or a double doublet, you do not have one coupling constant value, but in fact you have 2 coupling constant values, right? And this looks like this. So we have a doublet, and then we have another doublet. The relative intensity of the arms of this double doublet are 1, 1, 1, 1. That is because of the fact that you can see here no lines merge with others. So there is no merger of any lines, and so the relative intensity is 1, 1, 1, 1. Similarly, if we have this HB here, this HB has 3 protons in the vicinity. 2 are labeled as HA and 1 is labeled as HC. So HA, both of them are magnetically equivalent. They will have the same splitting or the same magnitude of splitting with HB, and HC will have a different magnitude of splitting. So HB will be split into 2 because of HC, and it will be split into 3 because of HA. So let's see. If it first couples with HC, it will give a doublet. So we start off again with a single line and split it into 2, and that is J1 because of HC. And then this HB couples with HA. Each of these two lines will be split into 3 because of these two HA. So you just draw a triplet as I showed you earlier. So a triplet from this one and a triplet from this one, and the coupling constant value would be different. So this is J2, this is J1. Just like for the double doublet, the J values are different. So again, we have 2 J values. So here we have another signal which is known as triplet of a doublet. That is a triplet originated from a doublet. So first we have a doublet and then we have a triplet. So we write it as DT, denoting the larger coupling constant. First you see the splitting between these two lines is larger as compared to these or these. So this is because of HC, that is a doublet, and here we have a triplet. So doublet has a larger coupling constant value and triplet has a smaller coupling constant value, and this signal would look like this. So we have one triplet and then we have another triplet. This is in a case when the magnitude of splitting for the doublet is larger than the triplet, but it may happen that it first couples with HA giving a triplet and then it couples with HC giving a doublet, and that is a case which looks like this. So if this HB first couples with HA, because there are 2 HA protons, it will be split into 3. So we have a triplet here. You can see the 3 lines here, just like the triplet I showed you earlier. And then each of the 3 lines of the triplet are split into 2 because of HC. So each of this line is split into 2 like this, right? And so we have 6 lines again, but this time the shape of the signal would be different. So we have a doublet like here, and then we have a larger doublet like this, showing these 2 lines, and then we have again a smaller doublet like this. So in all, this signal looks like a triplet which is split into 2 or doublets. So it's a TD or doublet of a triplet. But in the previous case, you say that this looks like a doublet which is split into 3. The relative intensity of the arms would be 1, 2, 1, 1, 2, and 1, because here we have the merger of 2 lines. In this case, this relative intensity would be 1, 1, 2, 2, 1, and 1, right? So this is how you can draw the coupling tree and the splitting trees. I told you earlier that it's very important to learn how to draw the splitting tree, because it will tell you about how to calculate the coupling constant. I'll tell you later on how you can calculate. So here it is, how to calculate the coupling constant values. Right, we have 2 peaks here, and we are going to calculate the coupling constants for each of them. First, we have this signal here, and it's a double doublet. You can see that we have 4 lines. It's a double doublet, and we have labeled them as 1, 2, 3, and 4. The chemical shift values are given here. So this is for 1, this is for 2, this is for 3, and this is for 4. As you just saw in the splitting tree diagram, that a double doublet has 2 coupling constant values. So we have to calculate 2 coupling constant values. But before that, before moving into calculate the coupling constant values, let me tell you how we can simply calculate the coupling constant for any signal. So if you have a doublet, for example, each of these arms will have their own chemical shift values. This one would have the higher chemical shift value. This one will have the lower chemical shift value if the scale is from like 0 to 10. So this is towards 10, it will have a higher value. This one is towards 0, it will have a lower value. So what you do is that you take a difference of these two, subtract the lower value from the higher value, and then multiply it with the frequency of the spectrophotometer on which analysis was carried out. So this is how you can calculate the coupling constant values. Now I'll tell you, or I'll take you back to the splitting trees here, and let me erase it. Okay, so we have the splitting tree. Now why it is important in calculating the coupling constant values, I just told you that if we have a doublet, you just take a difference of the chemical shift values of the 2 peaks and multiply it with the spectrophotometer frequency. Now in a doublet, we have these 2 lines. So you have to take a difference of these 2 lines. If I label them as 1 and 2, this is 1 and this is 2. So you take a difference of 1 and 2 and multiply it with the spectrophotometer frequency. Now for a triplet, how you can do that? Now triplet is because of coupling with these 2 protons. And this is equal to J, this is equal to J, this is equal to J, right? So what you have to do is that you have to actually take the difference of these 2. You cannot see these 2 lines in the signal because you have a triplet like this. So this triplet has these lines, these 3 lines above them. You cannot see these 2 lines. Now how will you know what is the splitting between these 2? Right? So you know that when these 2 lines were split, these were split with the same magnitude as the first one. So if this was equal to, say for example, 6 Hertz, this is also equal to 6 Hertz. To split this line into 6 Hertz, this line has to move 3 Hertz to the left and 3 Hertz to the right. And similarly, this one has to split by 6 Hertz and it moves 3 hertz to the left and 3 hertz to the right. So the distance from the center, or the distance from this line to this line, is equal to 3 hertz, and the distance from this line to this line is equal to 3 hertz. So we actually had to have 6 hertz, and here you can see 3 plus 3 is equal to 6 hertz. But you cannot see these two lines here. So what happened is that these two lines split, and that is why you cannot see them in the signal. So this one moved 3 centimeter to the left and 3 centimeter to the right, and this one moved 3 centimeter to the left and 3 centimeter to the 3 hertz to the right. So the distance between these two is equal to 6 hertz. So when you take a difference of these two lines, this is equal to 6 hertz, and when you take a difference of these two lines, 3 plus 3, this is equal to 6 hertz. If you want to calculate the difference between these two, you just take a difference of these two lines or these two lines. So a triplet will also have only one coupling constant value. So when you label them as 1, 2, and 3, you take a difference of 1 and 2 or 2 and 3 to get to the coupling constant value of triplet. So you don't have to write two values. In fact, you can write only one value. When you have a quartet, you see we have to actually take a difference of these two. And this is equal to J. This is also equal to the same J, and this is also equal to the same J. So when you have a quartet which looks like this, and you label them as 1, 2, 3, and 4. So the difference between 1 and 2 is exactly equal to the difference between 2 and 3, which is equal to the difference between 3 and 4. So no matter which difference you take, you will have the same value. So similarly, quartet will also have only one J value or one coupling constant value. But if you have this situation, so in this situation, we have a double doublet. Now, you do not have only one coupling constant value. In fact, we have two, J1 and J2. So you have to calculate both of them, all right? Now, you can calculate the J2 from here. So if you label them as 1, 2, 3, and 4. So J2 is equal to the difference between 1 and 2 multiplied by the spectrophotometer frequency, or it is also equal to the difference between 3 and 4 multiplied by the spectrophotometer frequency. But what about J1? How will you determine the difference between J1 or between these two lines, that is equal to J1? How will you calculate J1? Because you don't see these lines in the signal, right? You have 4 lines, but these 4 lines do not fall under these 2 lines. You don't see them here. See, this is empty. This space is empty. So what you actually need to calculate is the distance between these 2 lines, but you cannot see them in the signal. How will you determine what is the difference between these 2 lines? So you know that when this line was split, it was split equidistant to the left and to the right. So for example, this is equal to 6 and this is equal to 4, right? So you actually have to calculate 6 hertz. How? So when it moved to the left, it moved by 2 hertz, and when it moved to the right, it moved by 2 hertz, right? Similarly, this is also equal to J2, that is equal to 4 hertz. So if this was to split by 4 hertz, it moved to the left by 2 hertz and it moved to the right by 2 hertz. Now, the distance between this line and this line is equal to 4 hertz, but we need 6 hertz. How will you calculate 6 hertz? As I told you earlier, by calculation, that because these two lines do not merge, there is a gap in between, and this gap is equal to how much? See, the distance from the center to this line is equal to 2. The distance from the center to this line is equal to 2. And this center is right underneath these 2 lines, and the distance between them is 6. So if this is 2, this is 2, this gap is equal to 2 hertz. So the gap is equal to 2 hertz. This distance is 2. This is equal to 2. You need 6. Where is 6? 2 plus 2 plus 2. So the difference between 1 and 3 now is equal to 6 hertz, because from 1 to center this is 2, from center to 2 this is 2, and from this line to the third is equal to 2. So from 1 to 3 you have a distance of 6 hertz, or a magnitude of 6 hertz spreading. Or you can see from here as well, this distance is equal to 2, this is equal to 2, and the gap is equal to 2. So you need 6. 2 plus 2 plus 2 is equal to 6. So the distance between 4 and 2 is equal to 6. Or the magnitude between 2 and 4 is equal to 6. So you can calculate J2 from 1 minus 2 or 3 minus 4. And you can calculate J1 from 1 minus 3 or 2 minus 4. And the same applies to this. You can practice it yourself. You can calculate J2 from these two lines, or these two lines, or these two lines, or these two lines. But if you need to calculate this, see where it goes, where it ends up. So it starts from here, it goes down here, then it goes to the left, and then it goes again to the left. So this line actually ends up here. Similarly, it starts from here, then it goes to the left, down here, and then it goes to the left again. So it ends up here. So this is 1 and this is 4. So if you want to calculate J1, it will be the difference between 1 and 4. Or you can see it in this way. It goes down, it goes to the right, it goes to the right again, and it ends up here. Again, it goes down, goes to the right, and then it goes to the right, and it ends up here. This is equal to 3, and this is line number 6. So the distance between 3 and 6 is equal to J1. This is how you can do it. You can also take a distance of 2 and 5. And that will also be equal to J1, because 2 and 5 are exactly underneath these two lines. You can see, so you don't need to go to the left or to the right, but these are exactly under these two lines, and the distance between them will be equal to J1. So now let's move on to our peaks. So we have a double doublet here. This proton NMR spectrum was recorded at 500 megahertz. So in a double doublet, you can see that we have 4 lines. We have to calculate the coupling constant values, in fact 2 coupling constant values, and the coupling tree for the double doublet looks like this. So we have 4 lines, none of them merge with each other, and that is why you can see the relative intensity is almost 1, 1, 1, 1. How to calculate the first doublet and the second doublet? This is the larger doublet and this is the smaller doublet. The smaller doublet can be calculated from 1, 2, 3, and 4. The smaller coupling D can be calculated from a distance or a difference between 1 and 2 or 3 and 4. So you can see here J1 is equal to peak 1 minus peak 2 multiplied by the spectrophotometer frequency, or the distance between 3 and 4, the difference between 3 and 4 multiplied by 500. This will give you 1.5 hertz. That is the coupling constant for the smaller doublet. But what about the bigger doublet? We don't see these two lines. This is the bigger doublet. That is J2. We don't see them. So you go down and then go to the left from here. You go down and then go to the left. So 1 and 3. So the distance between 1 and 3, or the separation between 1 and 3, will give you the J2. Or you go down, go to the right, go down, go to the right. So 2 minus 4 will also give you the same value. So 1 minus 3 or 2 minus 4 multiplied by 500, 7.933 is 1 and 7.917 is 3. Multiply by 500 gives you 8 hertz. You can get the same value by the difference of 2 and 4. Now you come here, we have another signal. This is TD. So we have a triplet and a doublet. Triplet will have a larger value of coupling constant. Doublet will have a smaller value. So you can see 3 doublets actually. And for the doublet, you can see here that, let me draw the coupling tree here. It looks like a triplet. So first we have a triplet like this. I will draw it in short like this. And then each arm of this triplet is split into 2 like this. So you can see that we have 2 J values, this one and this one here. This value can be calculated by taking a distance or difference between 1 and 2 or 3 and 4 or 5 and 6. So J2 for the doublet will be 1 minus 2, 3 minus 4 or 5 minus 6 multiplied by the spectrophotometer frequency, that is 300 in this case, and so you will get 3 hertz in all the calculations. But if you want to calculate triplet, now where is the triplet? For the triplet you need a difference of these 2 lines or these 2 lines, but you cannot see them. Again, you just take them to the left or to the right. So this goes down and to the left, and this goes down and to the left. So 1 and 3. So the distance between 1 and 3 or 2 and 4 or 3 and 5 or 4 and 6 will give you the separation between these lines multiplied by the spectrophotometer frequency will give you the coupling constant for the triplet. You will understand it more when you practice it yourself, right? So just take this scenario with you and take out your spectra, calculate the coupling constants for all of these different types of peaks. So this is how you can calculate the coupling constants for different multiplets. Remember, the values are written in hertz. You might also find some peaks which are not clear. Their multiplicity is not clear. You don't know whether it's a double doublet, a TD, a DQ, a QD, whatever it is, but it's a complex splitting. For that, you cannot calculate the coupling constant values, or sometimes you see a singlet, but it's not a singlet, it's actually a broad singlet. So broad singlet cannot be taken as a singlet. It might be that this peak was a multiplet, a doublet, or a triplet, which was not split, and that is why you see it in the form of a broad singlet. For these type of peaks, we calculate the area under peak, or we also know it as the W half. So how you will calculate the W half? W half is the width at half of the height of the peak, right? For this, you need to do some calculations. So you take your scale and you measure the distance between the start and the end of the peak. So this is the start and the end of this peak. So area covered by the multiplet is equal to 10 centimeters, and you can do this with your ruler. Now from the scale here, you also put your ruler here and measure the distance, say from 1.5 to 1.6, and this is equal to 0.1 ppm. So this 0.1 ppm on your ruler is equal to 8 centimeters. So 10 centimeter would be equal to 10 into 0.1 divided by 8, that is equal to 0.125 ppm. If 8 centimeter is equal to 0.1 ppm, then 10 centimeter would be equal to 0.125 ppm. You multiply it with the spectrophotometer frequency divided by 2, you will get the value in hertz. Now 31.25 is the W half, or the width of the peak at half of the height for this multiplet, and this is taken in hertz. So this is how you can calculate the W half for complex splittings or broad peaks, taking help from your ruler. Now, what are the different factors that may affect the coupling constant value? So there are two major factors. One is the angle alpha, which is in a case when you have geminal coupling like this. So the angle between these two is the angle alpha, and from this graph you can see that as the angle increases, the coupling constant value decreases. So the information sharing decreases when the angle between these two protons, it increases. That is one factor. The second is torsion angle. Torsion angle is also known as the dihedral angle. So if we have vicinal protons and these are attached to sp3 hybridized carbons or any other type of carbons, now the dihedral angle is actually the angle between the two planes. So if you have two planes like this, and this is one of the carbon, this is the second carbon, and we have protons here and here, the angle between these two planes is the dihedral angle or the torsion angle. So if you close the book, the torsion angle is 0. When it is like this, the torsion angle is 90 degrees, and when it is like this, the book is wide open, the torsion angle is 180 degrees. And Karpel's curves gives you a correlation between the dihedral angle, the torsion angle, and the coupling constant value. So you have this curve, and you can see that when the torsion angle is 0, the coupling constant value is around 8 Hertz or 9 Hertz. But as soon as it increases, like from 0, it increases, it goes down. And when this torsion angle reaches 90 degrees, the torsion angle, the J value is almost 0. That is when they cannot couple with each other. And as soon as it goes beyond 90 degree, it starts increasing, and at 180 degree, the coupling constant value again is maximum. So if the two protons are at 90 degree from each other, then the coupling constant value would be minimum. So we have come to the end of proton NMR spectroscopy, and in the end I'll show you a proton NMR spectrum, and we will see all the parameters that we have discussed so far. So as soon as you have the proton NMR spectrum in your hand, the first thing you see is how many signals are there. So you can see here we have 1, 2, 3, 4, 5, and 6 signals. That means there are 6 sets of protons in this molecule. This is the proton NMR spectrum of acetyl salicylic acid, commonly known as aspirin, used in Dispirin tablets, right? And this is the structure of the molecule. And you can see from here that we can actually identify these different sets. So we have 3 protons here. This is one set. This one proton belongs to another set. This proton belongs to another set. This forms another set. This proton forms another set. And this OH proton forms another set. So we have identified these 6 sets of protons, right? Because of the fact that all of them, you can see they have different chemical environments, they have different groups attached to them, so their chemical shift values would be different, and you will see them separately, right? So we have 6 signals. Where do they lie? What is the chemical shift value? So we have a peak at around 2 ppm, we have peaks around 7 to 8 ppm, and we have a peak around 13 ppm. Now, if you remember from the proton NMR scale, we have discussed that the carboxylic acid proton usually is observed or seen around 10 to 12 or 13 ppm. So this peak most probably would belong to the carboxylic acid proton. And then we have this bunch of 4 peaks around 7 to 8 ppm. So that means that these might belong to the aromatic region. So we have 4 protons in the aromatic ring. You can see here, this ring is disubstituted. So we have 4 protons, and these are the 4 protons. And then we have this signal belonging to the methyl group. So when methyl group is directly attached to carbonyl, it will appear around 2 to 2.2 ppm. Normally, CH3 protons we have seen in the proton NMR scale, they appear from 0 to 2 ppm, and that is because this is connected to carbonyl, it will appear downfield, right? So this is the chemical shift value. You can calculate the coupling constant values, but we cannot see clear splittings between the when you zoom these signals, you will see clear doublets or double doublets here, and then you can calculate the coupling constant values from these chemical shift values given above. Another important parameter is the integration that we have not yet discussed. Integration gives you the number of hydrogens in one signal. So you can see here some figures, 3.18, which can be rounded off to 3, which means this signal is for 3 protons. This is equal to 1.05. So this signal here is for 1 proton. This is for 1, this is for 1, this is for 1, and here this is for 1. So if you add them up, 3, 4, 5, 6, 7, 8. So we should have in a total 8 hydrogens in the molecule. Let's see if we have 8. So 3 here, 4, 5, 6, 7, and 8. Right? So if you sum up the integrations from all the peaks, you will come up with the total number of protons in the molecule. So this is all about proton NMR spectroscopy. In the next session, we will talk about the carbon-13 NMR spectroscopy. We will see how we can read the proton NMR spectrum. I hope you have got enough information about proton NMR spectrum. Again, the only way you can understand this is to practice, is to study more and more spectra. We will have a practice session later on, and we will see how we can utilize proton NMR spectrum for structure elucidation. Thank you so much for now.